Hi everyone, my name is Lorenzo Zampieri and I'm a postdoctoral researcher at the National Center for Atmospheric Research. Today I will discuss a study developed in the framework of the M² Lines project and carried out with contributions from colleagues at the European Center for Medium-Range Weather Forecasts. In particular, I will present a machine learning correction model for the warm bias over the Arctic sea ice in atmospheric reanalysis. Many of us use reanalysis in our research because these products are quite convenient as they are continuous in time and space. However, when it comes to sea ice in atmospheric reanalysis, we should be particularly careful. So here in this sketch, I'm showing the typical model description of the ice and the snow on top of it. And normally we have a prognostic description of this medium, so it can evolve in time and space. And in addition, at the subgrid scale, we have discretization in ice thickness classes. This means that when the atmospheric model that's coupled to the sea ice model computes the heat fluxes, we normally have quite good idea of the heterogeneity of this medium. On the other side, atmospheric models that are used to produce reanalysis are typically uncoupled. And in this case, we have a very simple description of the sea ice system. In particular, we have a binary sea ice cover. This means that we don't really have a sea ice concentration, but we just have ice or non-ice. We have a constant ice thickness in time and space everywhere, no matter the hemisphere. And we also have no snow over the sea ice. Here I'm showing the typical thickness description in GRA 55, which is 2 meters, and ERA 5, which is 1.5 meters. And these are probably two of the most used atmospheric reanalyses in polar regions. A nice study by Batrak and Müller linked this very simple representation of the sea ice and snow in reanalysis models to substantial surface temperature biases that we will describe in this talk. The mechanism behind the bias is very simple and in fact quite intuitive. Just imagine a reanalysis where the sea ice has a constant thickness of 2 meters. In the real world, we can still find sea ice that's thicker than that. And we know that for this thicker ice, the vertical conductive heat flux will be lower compared to the thinner ice. This leads to a colder equilibrium temperature at the interface between the sea ice and the atmosphere. And normally the presence of snow exacerbates this, as we know that the snow conduces even less heat than the ice. Under these conditions, which are very common in the Arctic Ocean during winter, we will have a positive temperature bias, meaning that the reanalysis is too warm compared to the observations. Naturally, we can also have the opposite situation, where the reanalysis ice is too thick compared to the real sea ice. In this case, the simulated conductive heat flux to the reanalysis ice will be too small compared to the real ice, leading to too cold temperatures and a negative temperature bias. For example, let's have a look at this comparison. Here on top I'm showing some observations of the surface temperature. It's called skin temperature, so it's either the temperature of the ice if exposed or of the snow if there is snow on top of the ice. And these observations are from an infrared sensor. And the important thing to notice is that the atmospheric model used for the reanalysis does not assimilate this observation. You can see that the temperature, of course, it's not constant everywhere over the ice, but it has a certain distribution depending also on the weather patterns that are passing over the Arctic in this specific day, which has been chosen randomly. You see that the reanalysis temperature can somehow capture the shape of these weather patterns. However, the temperature is strongly biased. So you see there are these super large blobs, which here are saturated at 6 degrees, but probably are even larger. And this means that the bias that we can explain following what we discussed in the previous slide is quite substantial. The question is, can we do something about it? Also, please notice that this bias is not constant everywhere, but it's much more pronounced under clear sky conditions. In those occurrences, the surface can radiate much more energy to space and cool more effectively. And so we arrive at the core of this study, which is formulating an effective bias correction strategy. So as we saw before, the biases are state dependent, and in particular, they manifest themselves under clear sky conditions. And therefore, also the correction should be state dependent. In the past, there were some attempts to deal with these biases by adding a constant factor everywhere. But of course, this can also deteriorate reanalysis and doesn't really account for the complex weather that we can have in the Arctic. Also, another important point is that observations are not available all the time everywhere in the Arctic. And this means that we cannot rely on them to correct the reanalysis, because there will be periods over the reanalysis record where the satellite is not available, either because it's not passing over our grid cell in that exact moment, or because simply there was not a thermal image satellite in the past. So we need to find other predictors. And that's why we develop this bias correction strategy as follow. So we quantify the bias everywhere. We have observations, reliable observations. We also identify some predictors that can be linked to this bias. And these predictors can come from the atmospheric reanalysis itself. So for example, we can use the surface temperature as a predictor, or the downward long wave radiation, which normally gives a nice picture of the cloud state over the sea ice. But also predictors coming from other reanalysis. For example, we can use the sea ice thickness from biomass, or the snow thickness, which has recently been developed in the framework of the snow model LG. And once we find these predictors that can be linked to the bias, we developed a machine learning model, which basically is a very simple, fully connected neural network that links the predictors to the bias, and therefore basically is able to predict correction for the temperature bias. Before moving to the result part, I think it's important to clarify an aspect that's related both to the observation and to the bias itself. So we said that the cloud state is very relevant for the bias because in clear sky condition, it's particularly pronounced. But actually the cloud state, it's also important for the quality of the observations, because we don't have observations in cloudy conditions, since the infrared sensor would just measure the temperature of the cloud and not of the ice surface. That's why we decided to use only observations coming from clear sky condition regions. So basically, we need to be able, from a reanalysis point of view, to identify clear sky regions from cloudy cover regions. And you can see from these examples that's not really an easy task. For example, in the case of ERA5, we of course have reanalysis total cloud cover, but this looks quite overestimated compared to what's suggested by the observations, but also, for example, from a comparison with GRA55. And that's why we decided instead to diagnose the cloud conditions from the long wave state. On the other side, on GRA55, we get quite good indications about the cloud state from the total cloud cover variable, but the cloud contribution to long wave, it's much less clear over the Arctic Ocean compared to the ERA5 case. So now if we briefly go back to the comparison that I showed before, we see that it's more meaningful to compare reanalysis with observations only in clear sky regions that are shown as it's shown in this map. Now let's have a look at the surface temperature bias plotted as function of the predictors for the ERA5 reanalysis. The situation for GRA55 is not very different, so we will not discuss it here. So in the uppermost panel, we can see the bias plotted as a function of the atmospheric predictors, so the ERA5 skin temperature here at the bottom and the downward long wave radiation on the y-axis. And in the bottom panel, we see the bias in relation of the ice predictors, so the ice thickness and the snow thickness. We can observe some specific features. So as expected, a strong positive temperature bias is found for colder temperatures and also for thicker ice and snow, while we see a cold bias for thinner ice cover. Now, the correction factor predicted by the neural network reveals quite good skills. As we can see, the feature of the bias are well recognized, and obviously the opposite sign between the two columns indicate that the correction should cancel the bias ideally. Note that the network has been trained on winters from 2010 to 2018, when we have more observations to quantify the bias. And the subset that I'm showing here is randomly selected from a larger sample, which has not been involved in the training of the network, making this a real prediction of the correction. An interesting exercise that we can do is assessing which predictors contributed more to the model skill. And to understand this, we repeated the training by feeding the model only with either the atmospheric or the ice predictors. And we see that in general, the best correction model is obtaining by combining the two predictor types. However, we also see that a portion of the information provided by the ice and atmospheric predictors is redundant, and this can be interpreted with the consideration that we normally observe colder temperatures over thicker ice. And finally, we also see that the ice predictors are slightly more skillful than the atmospheric one. Now, if we go back at the reanalysis snapshot that I used as a case study for this presentation, we can see how the correction acts in clear sky region. So we can see a clear bias reduction, particularly in those regions experiencing colder temperatures in the interior of the Arctic. At the same time, we can also observe other regions where the bias is not reduced at all, or where we have also a slight degradation of the reanalysis temperature compared to the observations. Note that there is a certain degree of patchiness in the corrected temperature field, and this does not really come from the machine learning model, which produces quite smooth results, but rather from the application mask, which is related to the cloud state. And in particular, for the ERA5 reanalysis, the cloud state tends to be quite patchy and discontinuous in time and space, since we have high resolution both in time and space. We can now move to longer time scale, so leaving the observation aside, and have a look at the differences between the original and the corrected surface temperature when integrated over the whole Arctic. Here I'm showing the seasonal cycle for the 4 decades covering the reanalysis period that we considered in this study, and these are plotted in different colors here. We see that the correction brings the temperature down up to 1.2 degrees with a peak in winter, and basically a null effect in summer, where the temperatures are very close to zero anyway. We observe that the magnitude of the correction is also reduced in the most recent decades compared to the 80s and the 90s. And this feature can be interpreted by considering that the 2 meter for GRA55 or 1.5 meter for ERA5 constant sea ice thickness assumption in the reanalysis models is a better fit for the current sea ice conditions compared to the past. Finally, the last question that we try to answer is the following. Does the correction impact the warming trend of the Arctic as described by the reanalysis? To answer this, we computed the temperature anomaly for the corrected and uncorrected case, and we do this against their own climatology. And we see that the differences are very modest, both for ERA5 and GRA55. We see that the trend is slightly accentuated for the corrected dataset. So we see that the blue curve is a bit higher here and a bit lower here in the 80s. But the correction does not really impact the interannual variability, which I would say it's good news. Okay, so this is the last slide of the talk. Thank you for your attention. I want to leave you with this animation of the temperature correction for the ERA5 case, so that you can see how the correction behaves at an hourly timescale, which is the timescale of the reanalysis, and how it integrates with the Arctic weather pattern also at relatively short scale. So thank you again, and please don't hesitate to contact me if you have any question. Thank you.